Yes, let's continue with the concept. What is meant by conjugate acid-base pair? Okay, these are all called as conjugate acid-base pairs, right? Now, if I'm giving you a reaction, then how will you choose the pairs, right? HCl and Cl minus. After losing a proton, it will become Cl minus, right? So, how will you pair it up? HCl, Cl minus. Same way, H2O, H3O plus. H2O, H3O plus. So this makes a pair. Same way between these. Again here also it is HCl, Cl minus. And what is the other one? NH3, NH4 positive. Then you have CO3 2 minus with HCO3 minus and H2O with OH minus, right? You should be very careful which one you are choosing it as a pair. What is the difference between the species which make up a pair? Just a proton. Okay. See, there is a difference of one proton. Again, one difference proton ka difference hai. Isme bhi. Okay. So whenever you make a conjugate acid-base pair, see that the difference is only just one proton. Okay. So that's how you have to decide. Now, how do you get a conjugate base? Conjugate base is obtained when a proton is removed from a Bronsted acid. What is a Bronsted acid? An acid is a proton donor. Okay. उसमें से एक proton निकाल दोगे. What is left behind is nothing but conjugate base. Now say for example, HCl is a Bronsted acid. Now if you remove a H plus from this, what is left behind is Cl minus, right? So the Cl minus is the conjugate base of HCl. Same way conjugate acid is Bronsted base plus H plus. And what is a Bronsted base? Bronsted base is a proton acceptor. Okay. Now species which can act both as a Bronsted acid as well as Bronsted base. Okay. Species which can act both as Bronsted acid as well as Bronsted base. Now, how do you say that? See, now supposing you consider H2O. What will be the conjugate acid of this? After gaining a proton, what you get is the conjugate acid, that is H3O plus. And after removal of proton, what you get is the conjugate base of it, so OH minus. So how do you get OH minus from H2O? By the loss of proton. How do you get H3O plus from H2O? By adding a proton. So what you get by adding a proton is the conjugate acid. What you get by losing a proton is its conjugate base. तो इसका क्या होगा? एक proton remove करो तो NH2 minus. And here it will be NH4 positive after adding a proton. Same way HCO3 minus में एक H plus add करोगे तो H2CO3 बनेगा, मतलब carbonic acid. And this will become CO3 2 negative after losing a proton, right? Same way HSO4 minus, after losing a proton, SO4 2 minus is left. And after gaining a proton, this will become sulfuric acid. Okay, so this is what you have to understand, right? Now that is why you say species which can act both as Bronsted acid as well as Bronsted base. Okay, this can act as the Bronsted acid also in this form. It can also act as a Bronsted base in this form, right? Okay. Now all Arrhenius acids are also Bronsted acids because Arrhenius acids are also proton donors and Bronsted acids are also proton donors. But all Arrhenius bases are not Bronsted bases. This is a very important concept because Arrhenius bases are OH minus ion donor and Bronsted bases are proton acceptors. Okay. Now NaOH is an Arrhenius base because it can lose OH minus, but it is not a Bronsted base because it cannot accept a proton. Okay. Now let us see what are the advantages. How Bronsted-Lowry concept is better than Arrhenius. It is not limited to molecules, it includes ions also, right? So that is one. CO3 2 minus, we saw an example. OH minus is also there. Can explain the basic character of substances like Na2CO3, NH3. NH3 is a base. Arrhenius के हिसाब से NH3 base नहीं है. And Na2CO3 also, on the basis of Arrhenius you cannot say. But here you can say Na2CO3 is a base, NH3 is a base. Na2CO3 कैसे base है? Because Na2CO3 में से CO3 2 minus निकालो. Now, when it is adding up a proton, you will get bicarbonate ion. Okay, so this is the conjugate base, you can say, right? Can explain acid-base reactions even in the absence of solvent or in the non-aqueous medium also. But you can't say otherwise in the case of Arrhenius. Then what are the limitations? Reactions between acidic and basic oxides in the absence of solvent. Acidic and basic oxides in the absence of solvent. Acidic oxide, say for example, if I give you CO2 is an acidic oxide. Basic oxide, CaO, is a basic oxide. And what does it give? It will give you CaCO3. So this can take place in the absence of solvent. Same way, BF3AlCl3. They are not Bronsted acids, but they show acidic behavior. Okay, that means this Bronsted-Lowry theory is also having some limitations, because certain substances which act as acids you are not able to explain through Bronsted concept. Okay, so that is what is called as Lewis theory, that we will see in the next class.